Standard TCP/IP routing relies on two-dimensional meshes mapped across a Cartesian coordinate grid. When you force linear data vectors to move strictly along flat x and y axes, you guarantee physical traffic jams at central intersections. This diagram illustrates the bottleneck in large language models, exponential calculation, creating immense computational overhead on linear pathways. Throwing more hardware at this issue results in an NP-hard combinatorial explosion. As the network grows, the number of possible routing paths outpaces the physical processing speed of the silicon. The root cause is Euclidean flat space. Navigating 2D grids requires centralized tables, which inevitably causes structural coordinate drift and forces paths to physically cross at highly vulnerable data congestion points. The R4 prime router framework identifies network scaling constraints as a consequence of geometry rather than raw hardware performance. Standard hardware clock speeds cannot reach 1.2 terabits per second of throughput. Reaching that massive metric requires abandoning Euclidean geometry entirely and rebuilding the mathematical substrate of the network itself. The R4 framework addresses this by deploying a continuous, non-Euclidean geometric manifold. Rather than routing through external hardware gateways, it maps this topology natively onto local CPU caches. This removes the dependency on centralized, state-locked memory tables. Nodes coordinate autonomously based on their position within the manifold, processing updates relative only to their immediate neighbors. To enable this spatial geometry, the network treats prime numbers as continuous quantum wave states rather than discrete integers. By anchoring these quantum wave coordinates to specific multidimensional spaces, the system generates parallel transport channels. The arithmetic boundaries of these waves mathematically guarantee that the data paths never intersect. Embedding network nodes onto 4D hyperspheres replaces massive brute force search algorithms with the deterministic physical laws of geometric motion. To build this routing map, we must shatter the assumption that prime numbers are just random points sitting on a flat, one-dimensional number line. This visualizes the complex polar plane. Instead of plotting integers on an x and y axis, this system categorizes points using two variables: their distance from the center, which gives us magnitude, and their rotational angle, which gives us spin. The rule for magnitude in the R4 system is strict. A prime's distance from the center is dictated by the reciprocal of the gap between it and the prime that came immediately before it. This inverse calculation exerts a physical pull on the geometry. Massive prime deserts pull the data points inward toward the center, while frequent twin primes push the points outward to the edge of the grid. Once magnitude is set, the system assigns rotational vectors. If you use standard whole numbers to dictate the spin, the points immediately clump together into tight, predictable spokes that reveal nothing useful about the sequence. But by mapping those vectors to the exact reciprocal gaps, the random chaos of the integer line reorganizes into a highly structured, dense point cloud. Treating primes as harmonic wave emissions rather than static integers gives the R4 router a massive computational shortcut. It no longer needs to exhaustively count up an infinite timeline. It can mathematically predict the exact coordinate intersections where data channels will align. Those structured prime clusters on the polar plane function as the eigenfrequencies of a Hamiltonian system. The R4 router anchors this 512-dimensional frequency manifold across the first 512 non-trivial zeros of the Riemann zeta function, acting as a stable coordinate reduction pipeline. This equation illustrates the mathematical vulnerability of the manifold. When you map infinite continuous waves down into a discrete physical hardware system, you risk massive precision loss during modular reduction. The highlighted quantum parameter, n, exists specifically to set the exact precision boundaries of the ambient ring. As long as n remains strictly greater than the base 2 logarithm of x times y, the system maintains stability. By setting n sufficiently high, the modular discrepancy is eliminated. The framework achieves exact multiplicative coherence across the entire finite collection of values. Because this coherence is exact, the coordinate space can host universal quantum computation entirely within the temporal self-entanglement of a single photon. Translating that continuous spectral math into a physical machine requires a rigid hardware addressing protocol. The router operates on this discrete structural backbone, a hex-hive modulo 6 topology, mapping physical hardware MAC interfaces exclusively onto prime number coordinates. These coordinates operate strictly within the 6K ±1 residue class. The distribution of primes within this specific class provides a rigid mathematical guarantee. Parallel transport channels locked to these distinct prime coordinates will never naturally intersect. Projecting continuous spatial coordinates down onto these discrete prime indices completely eliminates coordinate drift across the hardware interfaces. Locking the hardware to the 6K plus or minus 1 class generates a deterministic, collision-free physical substrate. This discrete base layer is absolutely mandatory before the router can process the continuous non-Euclidean software running above it. Even with a perfect hex-hype substrate, keeping the physical layout in 2 dimensions eventually triggers geometric bottlenecks at massive scale. Dimensional elevation is required. The router deploys the Hopf angular routing protocol. It discards flat space addressing tables entirely and mathematically embeds the network nodes onto high-dimensional 4D hyperspheres. This stability constraint equation dictates a coupled field approach. Navigating a high-dimensional space requires balancing the static structural topology of the network with a dynamic latent potential field. The Ricci curvature describes the actual spatial deformation of the routing manifold, while the Hessian represents the variance of the steering field that pushes the packet along. A Laplace-Beltrami operator diffuses the signal density, allowing the wave-like propagation of information to flow across this curved space. To guarantee absolute mathematical stability as the network scales, the sum of that Ricci curvature and the potential field's Hessian must remain strictly negative. By utilizing the great circle distance alongside these continuous hyperbolic metrics, nodes calculate their routing updates locally and fluidly. The packet glides across the manifold without ever querying a centralized addressing system. The math holds up, but physical computing relies on hard empirical data. L2 normalized token embeddings on a hypersphere inherently cluster into highly specific regions. They are angularly non-uniform. This side-by-side performance chart shows what happens when the Hopf angular routing protocol exploits that non-uniformity. By deploying a fixed Hopf vibration map, it divides the hypersphere into fixed sectors, concentrating the tokens into a sparse subset of paths. The empirical result is a sublinear compute footprint. The routing slope drops from k to the power of 1 down to k to the power of 0.572. In practice, this compresses a 140 billion parameter brute force model down to a 70 billion parameter footprint, while maintaining exact processing parity. Validation tests on small trainable language models proved that fixing this geometric routing entirely replaces learned gating matrices, with only an 8% validation perplexity cost. On semantically structured data, a fixed 4D Hopf geometry demonstrably outperforms a standard 100-dimensional adaptive k-means clustering setup. The data proves that structural geometry inherently compresses logical workloads. A deterministic zero-allocation coordinate reduction pipeline vastly outperforms parameter-heavy probability matrices. Despite these physical benchmarks, the R4 framework faces intense academic scrutiny regarding its mathematical logic, most notably the logical conflation vulnerability. The foundation of the framework's math ties back to 1949, when Kurt Gödel proposed an exact solution to the Einstein field equations. It featured a rotating, homogeneous spacetime universe. Critics argue that mathematical models of rotating spacetime describe physical gravity. They do not natively describe the discrete logical states of a digital network. Applying Einsteinian gravitational metrics to multi-scale computer routing topologies requires heavy metaphorical lifting. A routing loop in a piece of software is a failure of logical state convergence that can be patched with a Bellman-Ford metric update. A closed time-like curve is a physical path through worked spacetime. Treating the two as topologically identical is a highly functional engineering metaphor, but it lacks physical basis. However, the physical benchmarks present a difficult counterargument. Regardless of semantic labeling, mapping the logic of topological gravity onto physical pathfinding functionally achieves sublinear scaling. The R4 router demonstrates that capabilities like data selection, compression, and routing are natural, emergent properties of the fundamental geometry of information.